So I need the residual to go away, and I need a procedure on how to do this, how to get this procedure, this residual to go away. And that's a little bit different than in standard Galerkin. It's a nonlinear projection now here, because it's a nonlinear method. Yeah? So the manifold of rank R matrices is not a subspace of the space of m by n matrices. It's a nonlinear subset. Yeah? So it's a manifold, in fact. And well, the idea is now I do a projection on the tangent space of this manifold. Yeah? So it's a nonlinear projection, and it's different in every point. Yeah? So I'm at the point YR, at one point in this nonlinear manifold of rank R matrices, and I demand that the right-hand side is in the tangent space of that manifold. Yeah? That's how I get rid of the residual. Yeah? So it's not the Galerkin projection. It's supposed to be orthogonal to the ansatz space, but it's now supposed to be a right-hand side that's in the tangent space of this manifold. Yeah? So that's a difference. It's a nonlinear projection, and it's different in every point. Why do I do this? Well, I want, that's now the name dynamical, I want my evolution to stay in that space of rank R matrices. And by doing this, I enforce that. Yeah? Because this is kind of a tangent vector, right, in a certain sense. So it points the direction in which my evolution goes. And I'm saying this evolution is supposed to this is supposed to be in the tangent space. Then the evolution stays in the space of rank R matrices. That's the whole point. Yeah, so that's why I'm making this projection here. Because if I make a different projection, I will run out of that space. Yeah, so that's the trick here. So project in such a way that I'm staying in that space. Yeah, so I'm refraining from trying to draw you pictures, but you all can think of a manifold, right? You have an evolution in that manifold. You have a tangent vector, and you want your increment, your time increment, to be. It must be in the tangent space in order for you to stay in that manifold. And if it is in the tangent space, you stay in that manifold. Yeah? So this is kind of the trick of the dynamical low rank method, I would say, in the beginning. Some other kind of projection. So now we need to look at the characterization of the tangent space. How do I look at it? How do I now turn this into formulas, right? Because this is very abstract. And I don't want to give you proofs, but just arguments on how this works, and I think you believe that it works like this roughly. So how does the tangent space look like? Well, I have the space is basically given by this. It's all the matrices that have a decomposition U as V transpose with an R by R matrix S. And I can just take this formula and differentiate it, if you wish, by the product rule. Yeah? So an increment, delta y, some infinitesimal one, will consist of three terms and a sum, and they are differentiated according to product rule. So an increment in u times s times v, an increment times s times u times v, and an increment in v times u times s. Yeah? So just product rule. Then the u, this is the space of orthogonal matrices. They satisfy u transpose u equals the identity. If I differentiate this, I see that an increment kind of has to multiply the original u, and I get 0. So I need to do this in the two different ways. But what I will later on demand is that this is 0. This satisfies this equation. Yeah? So an increment of an orthogonal matrix, when I multiply it with the transpose, gets me 0. Yeah? That's because of the orthogonality condition. So I stay in the space of the orthogonal matrices if the increments of these matrices satisfy this. Yeah? And that's kind of the trick if I use this, and it's a certain choice, it's a gauge to satisfy this one here. I can hit my equation here, for example, with u transpose from the left and v from the right, and I can recover the individual increments. That's the point. I don't want to go through this in all details, but using this algebra that I've written down here, I can solve this for the three different factors, yeah? For the increments in s, in u, and in v. And it's complicated formulas on the right-hand side, but it's just simple linear algebra. They are not too lengthy. Yeah? And that's now the point of dynamical low rank. So that's the first result. Namely, when I perform all of this, I've started with my matrix differential equation. I say I want to project my dynamics onto this low-rank manifold. I do this with this inserting the ansatz, nonlinear projection. And what I end up with, if I translate the increments into time derivatives, I have an evolution equation for S, for U, and for V. Yeah? So I've turned this into a system for the individual factors in this low-rank decomposition. All right? And that's huge, actually. Why? For several reasons. So for one thing, I do not have to determine my optimal bases in a certain way. Yeah? So in a way, U and V contain orthogonal bases, yeah? Or orthonormal bases, and I have an evolution equation for them. Yeah? I start with some bases, and the system itself, over time, will select the best bases in which to describe my solution. That's kind of cool what it can do. Yeah? So I don't have to do this by an SVD or something like this. I might have to do this in the beginning to start with an optimal basis, but then it just evolves them into, it keeps them in the optimal basis. It's not going to be true in the end, but for now it's true. Yeah? So here, this is the way this goes. And I have an evolution equation for the S as well, for the expansion coefficients. Yeah? So that's awesome, and that's why it's called dynamical low rank. So it's not a low rank by SVDs, by throwing stuff away. It dynamically evolves everything in time. Yeah? So that's what it does. The second point from a more practical point of view, I have a reduction in computational effort and more importantly in memory. Because if I look at these objects, the original object was size m times n. Yeah? So discretization times discretization. These objects here are much smaller. This is m by r, this is n by r, and one that's r squared. So I've turned something that's quadratic into something that's linear. Yeah? So think of a simulation which is 1,000,000 by 1,000,000. So if I can do, I'm going to show you that sometimes I can get by with rank 10 and 20. So it's now 1,000,000 times 10 or 1,000,000 times 20 only. So these objects are much, much smaller. Yeah? And again, memory being much more important these days than computational effort. That's even huger. Yeah? So these two selling points for dynamical low rank. Yeah? Any questions so far? So I do see some feedback from actual faces, again, which is nice. It's not cameras turned off by Zoom, so I have a feeling that you can follow. Let me now, I didn't give you the dirty details. I should maybe tell you something about dirty details now before I go to the computational results and we look at them until we're done here. So the dirty details are that actually this formulation is unstable numerically, unfortunately. And that's because I have an inverse in here. So especially if the solution is close to low rank, I will have small singular values. Yeah? I cut them off at some point, but the inverse kills me. Yeah? So small singular values turn into large ones here. So in fact, this system is unfortunately unstable. Yeah? And you need to do, so this comes from the chemical engineer or quantum chemistry. So they've done ways to circumvent this. There is actually now a version of dynamical low rank that has been developed, and I think I have some papers in the end. It's developed by Christian Lubich in Tübingen, an ODE guy, which does not have the inverse anymore at the price of having QR decompositions and SVDs. So it's not perfect anymore in the sense that it evolves the basis. I need to get the basis out of QRs and SVDs, which, however, still satisfy this. It's not just the pure magic of dynamical low rank anymore. Yeah? So I can remove the instability, but I have to do additional singular value decompositions in the integrator. Nonetheless, still a pretty cool method, I would say. Okay, there are no more questions, so I think we can start the picture show for the end. Kind of, you can now look at things and tell me when to stop, right? But it's the relaxing picture show in the end. So let's look at some of the methods and how they perform. Yeah. So I think I start with dynamical low rank and then I go to the other ones. First, is dynamical low rank working here? So I did not mention all of the things that you need to check, but one of the questions is how can I expect my solution to be of low rank? One answer is if it's smooth, yeah, then the coefficients decay fast, and you have a chance of having an accurate representation, but there are other possibilities where it might be low rank. So essentially it means that it has a product form. Yeah? So if your solution, say it depends on x and psi, if it can be expressed as a term in x times a term in psi, that's rank 1 already. Yeah? So it has, if it has a product structure or something close to it, that's low rank. But anyway, so let's just try and see with how many ranks we can get by. So here's uncertain burgers again, two-dimensional uncertainty, namely the point where the discontinuity is also uncertain, and this is the one we had already. Yeah? So the jump height is uncertain, so the right state varies, but this time also the position where the initial shock starts. Yeah? 2D uncertainty, 1D in space. And here you see some numbers. The points in X are 600. I think this was done with the first order method, but it doesn't really matter anyway. And it's done with 100 degrees of freedom in random space. Yeah? So this is a 600 times 100 matrix. I need to use quadrature rules in between, so it's 256 quadrature points, which you can also factor into this game. And we get by with rank 9 later on. Yeah? So it's a reduction by an order of magnitude, actually, in memory and in computational effort. I hope you can see some stuff here, but it's basically lines on top of each other. So that's the expected value, and we kind of saw this expected value before. So it's now a line followed by a straight line, and this you still get even in this two-dimensional case. So that's my exact expected value. You see a stochastic Galerkin computation with, it has index 324, which I don't know what it means, but actually the parameters are different than what I just said. That's kind of stupid when I did this slide. So it's 1,000 spatial cells. It's 18 squared moments, which you can compute, which is probably 324, I guess. So it's 1,000 by 324, and we can get by with rank 25. Yeah, so I should remove the numbers from the previous slide. So now you can throw chalk at me because, again, I didn't understand my own slides. But I understand them again. Well, what you can kind of see is that these methods oscillate a little bit. You can see this best here, I think, because they're still based on polynomials, right? But it's a high order degree, so they oscillate just a little bit. Yeah, this is not IPM here. This is pure stochastic Galerkin. But you can see that dynamical low rank is not that much worse than the original one. Yeah, so you have a reduction by a certain factor in terms of memory. The points where you see a big difference is kind of here, where this is the onset and where this is the offset. But this is, I think, a reasonable solution at a big reduction. Not so much in computational cost. I think that's only a factor of 3, but in terms of memory, it's a bigger factor. It's a factor of 10. That's more important. It's a bit more scientific than just showing you lines on top of each other. That's an efficiency plot. Some details here is basically the same setting and different ranks, I think. So you see a log plot of the runtime in seconds of that implementation we have. And here's the relative error and the expectation. Yeah? Again, relative being much better than absolute error. And here is the variance. Yeah? And you kind of see this is the convergence of the stochastic Galerkin method, right? So if I run longer, I go to a smaller error because I've cranked up the number of points in random space. Yeah, so this is along this convergence. It starts at 4 point, ends at 324. And you see the rank 25 solution with increasing discretization, which is about a factor of, I don't know, 3 or so faster than the original one. Yeah, it's not a factor of 10 that you have in the memory, but a factor of 3, roughly. And you see this both in the expectation and in the variance. Pretty much the same picture. Yeah?
And so the rank always increases when you increase the
No. If I start with 4 points, it doesn't make any sense to say rank 25 because then I'm doing nothing. So the rank also increased. Yeah. Don't ask me how, unless this is written. The rank takes values from 2 to 25. How it was done, I don't remember anymore. That's also possible, but that one wasn't done here. So you can also do this adaptively. You could do it adaptively, yes. But that wasn't done here, I think. Yeah.
So here usually you would have to determine beforehand the maximum rank,
Yes. In a certain sense, this is kind of experimental in a way, yeah. But again, so there's rank adaptivity, yeah. So that exists actually. To start with some rank and then it basically increases or decreases the rank by itself. Yeah. Yeah. Okay. Another pretty picture. So this addresses, I think, adaptivity in random space, as far as I know. So it's a pipe flow. So essentially, it's a Riemann problem in the pipe. I think it flows from here to here, and I have high density region and I have a low density region. I have an initial shock position here. I have densities on the both sides, and I think I'm solving the Euler equations here. Yeah. So density above 1.3. Energy above 1.0. It's a two-dimensional Riemann problem on this bent pipe, and an uncertain position of the discontinuity and of the density and of the energy below. So it's three-dimensional in random space. So I have psi 0, 1, and 2 in this case. Yeah. So it's two-dimensional in physical space and three-dimensional in random space. Yeah. And it was done using IPM, so in this intrusive polynomial moment method with adaptivity. And what you see here, and on the next one, I think you see the adaptivity. So this is how it looks like. So this is flowing in this direction. So you still have the shock moving in the pipe, but because it's bent here, something is happening, right? So in a flow, if it goes around a bend, things happen, high density regions form and so on. And you can kind of see this by this expected value, yeah? You have a higher density here in this band. And also, what's interesting is, the variance, the prediction of where the code believes it's uncertain, and that's precisely here in this band region. Yeah, so it generates a lot of uncertainty in this very problem that I'm starting with. And it's not so much uncertainty in where the shock is, yeah? But it's actually at the bend where this is uncertain. But these pictures are maybe not so important. It was computed using adaptivity in the random space. Yeah, so you see here the different refinement levels in random space, which are actually discrete values, 0, 1, 2, 3. And so it's cranking up polynomials. Yeah, so I'm on a three-dimensional random space, and here I have 4 moments, which is just the constant plus the linear. Then I'm taking in the quadratic, the cubic, and the quartic. Yeah, I hope the math is right here. Yeah, oh yeah, it says it, degree 1, 2, 3, 4. Yeah, so this is how I crank up the hierarchy in moment space. Yeah, three-dimensional moment space. And here you see a statistic in the steady state, how many cells are in which category. Yeah, so you see a lot of cells in the very low category. You do see a significant amount of cells in the category with the highest degree, and so on. And you can kind of see the number of degrees of freedom that you have, and you save a factor of 3 roughly. And it's also interesting where it refines. There's nothing here where there's just outflow, which is kind of expected because stuff just leaves the pipe. It's an interesting region here, so the indicator oscillates a little bit. So it says, am I troubled or not? Yeah. So it's just basically changing between 0 and 1 in terms of the refinement. And then you see here, interestingly, in the region around the big uncertainty, it tells me, hey, here I need to refine. And here it's also kind of cautious in that region. Yeah? So it's cautious around the bend. Yeah? So it's interesting, pretty pictures. I'm selling T-shirts with this picture later on, and I sign them as well. Just it's 15 euros. Special offer. And then maybe the last one. This is the flow around the Naka profile. So again, walking you through the details, you see it's an unstructured triangular grid. We do not have adaptivity in that grid. That would also be interesting, of course. So it was a grid that is, of course, designed to capture the stuff that's interesting, right? So this is where the shock is forming, so it's finer there. And it gets, gets coarser when I move away from the wing, actually. And remember, the actual domain wouldn't fit into this building, I think, right? So the grid goes up very high. You saw in the initial picture. So about 20,000 elements here, refined in interesting regions. This back then was first order. I think we have a higher order code in space now. So it solves IPM, and IPM you can also parallelize a little bit. Yeah, it's not embarrassingly parallel, but you need to solve optimization problems in each of these cells. So in that sense, it's parallel, right? So I have my state in a cell. I need to reconstruct this minimum entropy distribution. That I can do perfectly parallel in every cell. So it does the quadratures and the optimization problem totally in parallel. Then, of course, I have to gather the information again, wait a little bit. So I still need to do load balancing and all of these things, but it is parallelizable in a certain way. Yeah? So that's MPI parallel and OpenMP in space, which of course can also be improved, but there is a certain sense of parallelizability in this thing. And again, so that's kind of a frame of this course. So I started with this example and going to finish with this example. This again also for the people that were not here in the beginning. So this is the expected value now under an uncertain angle of attack that I haven't written down again. So basically the flow comes from here roughly, and the angle of attack is uncertain. Yeah, so it's equally distributed around 1.25 degrees plus minus something. Yeah? And there are the usual things happening, right? Something happening at the tip, a discontinuity here above the wing, some rarefaction below the wing, and so on. Yeah? And the interesting thing is to look also at the variance, and there are some things that are expected and some things that are unexpected, I would say. So where the discontinuity is, there's a lot of variance, right? And first of all, it's smoother, right? It's not a shock anymore, and I don't need to do shock capturing. That's kind of the point here. So I can potentially get by with a smaller resolution here, and potentially a higher order method, which we haven't implemented so far, but nonetheless. So it's smoother here, but still the position is kind of uncertain, so lots of variance here in this region. A lot of variance also here at this rarefaction wave, and interestingly, very little variance in certain regions here. In that region here, in the region before the wing, which I find interesting. Yeah. So well, maybe the wing doesn't influence that much anymore, but there's actually this stuff at the tip. And interestingly here, little variance, and of course in the tail region there's little variance. Yeah. So some features that I expected, but also some that I find quite interesting in what the uncertainty quantification tells me for this problem. All right, and then, okay, this was done adaptively, so kind of the same picture as before. The T-shirts on this one are sold out, unfortunately, but you can order them in the online shop. Again, so here's the statistics. So this is only 1D in random space, 2D in physical space. So I have linear increase in the number of moments that I've taken, yeah, the order of polynomial that I take. And again, the statistics is kind of similar. You see a lot of cells in the lower regions. Yeah? Then you see not that many cells in the intermediate regions, but then there are, again, regions where it gets interesting, so where it cranks it up very high. So that's a typical picture that you kind of see in adaptivity also for hyperbolic conservation laws. I would say this is not very surprising. Yeah, so this, of course, has a lot of refinement where the discontinuity is, and a lot of refinement where this other structure here is. Yeah, so the rarefaction wave down below In the tail region, there's not that much. In the region leading up to the wing, there's also not that much. Yeah, so it's kind of reasonable, but it still looks pretty, and it's nice that the code does this all by itself. All right, then not that pretty anymore, but I talked to you about one-shot and adaptivity, right? How does this show in terms of the runtime? So runtime here, linear scale this time, and this is the accuracy. So by cranking up the different orders of random space, I get these different pictures. And they reach a certain accuracy after a certain computational time. So if I move to the left, better, of course. Left bottom is better here. And what you see is a pure IPM solution. So that's the green one. You might also say if we had a better indicator of stopping it, we should have stopped it here probably, because at this point in the computation I was pretty much done. But then you see that the different methods push you a little bit to the left. Yeah. So the orange one is this one shot of nesting the iterations, yeah, iterating into steady state together with the entropy. This saves whatever, a couple of thousand seconds actually. Then we have the purple line. This is just adaptivity. Yeah, so this is better in a certain sense than one shot. So it shifts you, I think, by more than 10,000 seconds. So more than 20% in this picture. And then ADOS, the red one, is combining both. Yeah, so I have adaptivity and I have the clever iteration into steady state. And if I compare this line to that one, so here I'm actually at 40,000 and here I'm, yeah, well, maybe this one is 10,000 seconds, so a quarter that it shaves off. The thing that's not nice here is that this is a stochastic collocation solution, but the random space is only one-dimensional here, and it looks actually better. Yeah, so that's, to be honest. Qualitatively, however, this solution does not look that good. Quantitative, it's good. It oscillates heavier than the other ones because the other ones are IPM. Yeah, so that's actually something that suffers from oscillations. But in the norms, it looks better. Yeah, that's just, to be honest, about this, because I don't need to solve all of these optimization problems all the time. Right? It's a simpler method. However, we expect that if this is in higher dimensional random space, that ultimately this can be beaten. Yeah. So similar picture for the variance. I don't want to go into too much details, but it's kind of the same. Yeah. IPM can be improved by adaptivity more than one shot. Yeah. So adaptivity also works in the time-dependent case. One shot only for the steady case, and putting them together turns it into something that's at least computationally competitive with a stochastic collocation solution. Yeah. And it's L2 error. Yeah, so here, well, there are some pictures which show you that maybe qualitatively you would prefer the solution that IPM computes because it does have less oscillations, yeah, for a price. So this is stochastic Galerkin with 10 moments in this case. And you see the error in the density. And in this case, it doesn't suffer from the loss of hyperbolicity, but you're just lucky. Yeah? So in this case, it runs through. Even with Euler, you don't get into any states where your numerical method blows up. It's not a hyperbolic system strictly, but the method works. In other cases, it blows up. Yeah? For Euler, you need to take a square root somewhere typically. And with this one, you get into trouble, potentially. Yeah? But so you see the error. The error is mostly in this region of the shock, and it's kind of oscillatory a little bit, yeah? Which kind of tells you that the stochastic Galerkin solution, being consisting of polynomials, oscillates where the shock is. Yeah? So Gibbs phenomenon. That's the comparable intrusive polynomial moment solution at the same order. Yeah? Again, much more expensive because I need to solve this entropy minimization problems, but looks much better. Yeah, so the same color scale as the previous one, and the colors are much smaller, and it's a little less oscillatory than the previous one. That's the variance. The variance is a little bit more boring, actually. So that's stochastic Galerkin with 10 moments. The variance is not that bad anymore. I am aware that one should plot the standard deviation, but, and I keep telling this to my students, but I don't do plots myself, my students do them, so this one he hasn't redone in terms of the standard deviation. But anyway, so it's a quadratic thing, that's also why it looks less, yeah, in a certain sense. But IPM looks again a little bit less than before. Yeah. So, that brings me to the conclusion. If you want to read a little bit of literature, so I will send around the slides. Yeah, you can also have them. If you want to read a little bit about dynamical low rank, this one would be something that's interesting, I guess. If you want to read some of our stuff, dynamical low rank for kinetic equations, these intrusive acceleration strategies for IPM, all the gory details about how you actually get it to run in a stable way. Feel free to look at these papers and feel free to ask me questions. And the dynamical low rank for burgers is even a preprint. Yeah, so again, the whole course, well, anyway. And here is, that's another preprint. The rank adaptivity that Michael is talking about is also new in a certain sense. Yeah. And that brings me to the conclusion. So again, so what was the idea of this whole course? Yeah, I gave you some general introduction and then went to my own stuff. I think that's the way everybody does that here, you know. So I think the combination of uncertainty quantification and hyperbolic conservation laws is still interesting. Yeah, so maybe some of you want to look into this in the near future if you do either one of them. Yeah, so looking into this other field and doing combinations is worthwhile because hyperbolic conservation laws are very special in their smoothness structure. So they're interesting and have a lot of structure. You know, entropy, hyperbolicity, the lack of smoothness in your solution. All of this make it an interesting field to do mathematical or computational research. Yeah. And again, I showed to you that it's maybe worthwhile to look into intrusive methods. Yeah? I'm not saying you have to do it. If you want to do a quick uncertainty quantification, you're allowed to do Monte Carlo from my side. That's fine. You can do multi-level Monte Carlo, all of these things. But maybe, just maybe, intrusive methods might be something to look at. Yeah? And then if you look at them seriously, you are first shocked by them not having hyperbolicity. That can be fixed at a price, yeah, of solving these optimization problems. And I don't think there's another systematic way of doing this. Yeah? So there's ways to do this in certain examples, right? Sometimes you're lucky, but this is kind of the general way to do it. It's foolproof in the sense of, on paper, it works always. Difficult to put into practice, ill-conditioned problems, expensive, you need to do a lot of work, but that's also what makes it interesting, right? Because there's a lot of techniques that go in there, ill-conditioned optimization problems, computational issues, load balancing, adaptivity, all of these things. So a lot of the techniques that one learns in the classes at university you can apply, which also make it interesting, right? And you can try to get it to work. And then there are many strategies also, kind of the standard strategies that one can use here in principle, namely this nested iterations, you know, play with that, play with adaptivity. And a rather novel thing is to use model reduction techniques. One of the most promising, I think, is dynamical low rank because of the things that I told you. And the outlook, well, if you want to know my opinion on what research can be done, I mentioned some of it, but let me just read the slide just to not forget everything. There are quadrature sets involved. You can do adaptivity for those. It's a big question of doing the load balancing, right? If I have adaptivity at some point in space, how do I distribute this over my processors? Smoothness indicators for adaptivity, combining this with higher orders, and ultimately answering the question that I've just raised in the beginning, and we're trying to do this, with how much less shock capturing can I go, right? So if I do a fair comparison of a non-intrusive method, yeah, how much shock capturing do I need in order to approximate my expected value? Yeah, because my individual solutions will have shocks. I afterwards, in the post-processing, put them together to an approximation of the expected value, which is smoother. Yeah? Versus I approximate by an intrusive method the expected value directly and hope that I can get by with less high order, less shock capturing. But kind of the verdict is out there, and that's certainly an interesting question to answer in a fair way, yeah, because implementation issues go into this. That's it. Thanks for being here. Thanks for providing a physical audience. It was very nice for me. And I hope also for you. and it's nice to have people clapping on the tables, not just virtual hands. Yeah.
Yeah, thank you very much. Nice presentation. Any questions?
Yep.
You also look into the time-dependent flow around the data profile?
We have not done that yet. To answer this, we have looked at the steady state in this paper because we have this one shot, and the one shot only works for the steady state, right? So this is where it came from. But of course, the code that we have, it's a time-dependent code, right? It could, in principle, solve the time dependence, yeah. But I don't have any results here, actually. Yeah.
And if you make an error in solving this optimization problems, do you then lose mass or do you have any trouble with the other properties of the conservation law?
Yeah, well, I mean, that depends on the formulation. So if I use this, I do a reconstruction in every cell. Yeah. So I have moments in random space, and I basically get my ansatz out of it. Yeah. So assume this ansatz is not correct. What I only use this ansatz for is to compute the fluxes over the cell boundaries. Yeah. So in that sense, it's still a conservative method. Yeah. So I don't use conservation. I just lose accuracy. That's what I do.
And maybe positivity.
There are fixes for the positivity as well. But no, I would say, I mean, the solution still has this exponential, right? Which is positive. The reconstruction is positive, so that's not an issue, really. I'd say, because you just get inexact Lagrange multipliers. You plug it into the exponential, it's positive by definition, so that's not an issue.
And which entropy do you choose?
I mean, yeah, that depends. I mean, if you're free to, so the question is if you're free to choose it or not. I mean, if you do two-dimensional Euler, you take the Euler entropy. It's unique in a certain way, right? Up to certain transformations, it's unique, so you need to take that one. If it's a scalar conservation law like Berger's, if you have a liberty, then you can decide, right? So we basically took for Berger's one that mitigates oscillations. It's one that enforces a maximum principle, and by enforcing the maximum principle, it makes the polynomials oscillate less. So if you're free to choose it, I think a version of f log f is quite smart to do.
So I remember that there was a concept here, this is possibly correct, where you have this admissibility set for
Yeah.
this is also an issue now.
Mm-hmm.
And it's much more complicated with this higher dimension problem.
Yeah, it depends. I mean, if your uncertainty is from 0, 1 to the d, the hypercube, it's easier.